You ever stop and wonder what's really going on inside your coffee maker? Or your digital watch? Or even your car's remote? Well, there's a tiny hidden brain running the whole show, a microcontroller. And today, we're going to take a tour of its mind to uncover the secrets behind its absolutely incredible efficiency. So here's the central question, right? How do these really simple, low-powered chips make all the little decisions that basically run our world? I mean, they don't have massive hard drives or tons of memory to work with. The secret, it turns out, is all in how they're organized. To really get this, we're going to use an analogy. So, for a minute, just forget about lines of code. Instead, I want you to picture this memory as a tiny, perfectly organized workshop that's been designed for one thing: maximum speed with minimum waste. So, come on, let's step inside. Okay, so any good workshop needs a clear layout, a blueprint. We're going to be touring the internal memory of a true classic, the 8051 microcontroller. You can think of it as our floor plan, and it's divided into a few key areas, each with a very, very specific job. Our tour is going to cover three main zones. First up, we've got the quick access toolkits. These are all about speed. Then we'll check out the individual switchboard, which is for super precise control. And finally, there's the general workspace, which is kind of for everything else. So let's start with those toolkits. You know, in any workshop, you keep the tools you use the most right beside you, right? It just saves time. That is exactly what these quick access toolkits are for. Now, the technical name is register banks, but all you need to know is they are designed for one thing and one thing only: pure speed. Okay, take a look at these two commands. They're both trying to do the exact same thing: get the data from memory location number 5. But they go about it in totally different ways. The command on the left is this really clever shorthand. It's basically saying, hey, just grab tool R5 from whatever toolkit is currently active. The one on the right is way more direct. It's like saying, go all the way to the specific shelf location labeled 05 and get the tool. So why does this tiny little difference matter so much? And here it is. This is the brilliant payoff. The shorthand command takes up only 1 byte of precious memory, while the direct command takes up 2. It is literally half the size. Now, in a tiny system where every single byte counts, a 50% saving is absolutely massive. It is just a simple, elegant trick for working faster and lighter. All right, on to the next part of our workshop. See, sometimes you don't need a whole toolkit. Sometimes you just need to flip one single switch. This area of memory, which is known as bit addressable RAM, is like a massive control panel with hundreds of tiny individual switches on it. So the whole point here is precision. Let's say the microcontroller wants to turn on a single little warning light. It definitely doesn't want to mess with the other 8 lights that might be connected to the same circuit. This switchboard lets it flip just one bit, one single switch to on or off, leaving everything else completely untouched. This is the absolute key to fine-grained control. And now we've arrived at the real heart of the workshop, the master control panel. These are the special function registers, or SFRs for short. They're not for general storage. No, you should think of these as the main dials, levers, and status meters that control the entire operation. We're going to look at 3 really key examples. First up is the stack pointer. Now, I know it sounds technical, but just think of it as an automated helper. Imagine the chip is right in the middle of a big job, and suddenly it gets interrupted by something way more important. It needs a place to quickly and safely set down its current work, right? Well, that's what the stack is for. And this is how it works. When the chip issues a push command to save something, our little helper, the stack pointer, first automatically finds the next available empty spot on the shelf. Then it just places the item there. It automatically keeps track of where it left everything so the chip doesn't even have to think about it. It's simple, it's automatic, and it is incredibly useful. Okay, next up on our control panel is the Power Control Register, or PCON. This is basically the energy-saving switch for the entire workshop. And for any device that runs on a battery, managing power is, well, it's everything. This one register lets the chip put itself into different sleep modes to save energy when it's not busy. It has 2 main modes. In idle mode, it just turns off the main brain, the CPU, but it keeps other things like timers awake. It can be woken up really quickly by some external event. But in power down mode, it shuts off almost everything to save the absolute maximum amount of energy. The only way out of that deep, deep sleep is a full reset. So it's always this trade-off between saving power and being ready to act at a moment's notice.
Our final stop on the control panel tour is the Program Status Word, or PSW. And honestly, the best way to think of this is a bank of indicator lights. After every single calculation the chip does, these lights update to give it an instant snapshot of what just happened. And that snapshot is crucial for making its next decision.
So what are these lights actually telling us? Well, the carry flag is kind of like an overflow warning on your coffee cup. It lights up if a calculation's result was too big to fit. The parity flag is just a simple error check. It confirms if the result is structured correctly. And the overflow flag warns if a math problem created a weird, unexpected result. These little flags give the chip instant feedback on its own work. So, we've toured this tiny, elegant workshop. And you might be thinking, okay, this is all about old, simple tech. But the real genius of this design is that its core principles are actually more relevant today than they have ever been. This design philosophy is over 40 years old. 40 years. In the world of technology, that is an absolute eternity. And yet, the foundational ideas we've just walked through, they're still at the very heart of how even the most modern processors work. Just think about it for a second. The idea of having quick access toolkits for speed, a switchboard for precise surgical control, and a master panel to manage the system's state. These exact same concepts of efficiency and specialized function are what allow that incredibly complex processor in your smartphone to manage billions of operations per second without just melting or draining your battery in 5 minutes. And that leaves us with a really fascinating question to ponder. We've seen how these elegant, resource-saving designs from decades ago literally formed the blueprint for today's tech. But as we push forward into an age of AI, quantum computing, and devices that are just infinitely more complex, will these simple, brilliant principles of efficiency still be enough? Or are we going to need a completely new kind of workshop?